There we are, good. I can go. So I'm going to be talking about what we can learn about galaxy formation by using information from discrete tracers in concert with the information we get from the galaxy starlight itself. And this work's done under the umbrella of the SAGES collaboration, and these are many of the collaborators on this project, and the people in yellow here are at this meeting. So I'm going to try and set the stage for a number of topics that will come up in talks that will be given by group members later on in the week, this afternoon and Thursday, in fact. So one of the reasons we really like globular clusters, or among the reasons we really like globular clusters for understanding galaxy formation, is, of course, because almost all galaxies, except the very tiniest ones, have globular cluster systems. And the premise is that globular cluster formation accompanies all the major star-forming episodes in a galaxy's history. They're bright compared to the underlying galaxy starlight, and once formed, they're really unchanging. They're formed at very early times, they're unchanging, and are along for the ride, if you like, with all of the mergers and acquisitions that come to build the galaxies we see today. So because they're bright, we can do spectroscopy to pretty significant distances. So everything I'll be talking about has come out of the SLUG survey. This is a survey done with Subaru and Keck, particularly the DEIMOS spectrograph, of 25 nearby early type galaxies. And these galaxies have a range of fundamental properties. And we're able to look at the field stars out to 3 effective radii and the globular clusters to 10 or more effective radii in these galaxies. So we get 2-dimensional kinematic and metallicity maps with which we can compare to the theoretical models. So we completed the observations just this year, and we already have about 60 papers that have resulted using data from this survey. And I invite you to have a look at the website here to see the wide variety of things that we're doing with these data. So there's a couple of things you need to know about globular clusters as discrete tracers in the galaxy formation context. One is that they're bimodal in metallicity. This is a color histogram up here, clearly bimodal. They're also bimodal in metallicity. These are spectroscopically determined metallicities. And this tells us that there's a metal-rich and a metal-poor subpopulation in the vast majority of massive galaxies. And some work that was led by my then postdoc Vince Poter, we've demonstrated that the subpopulations are not only distinct in metallicity, but they're also kinematically distinct. And this is just VRMS against radial extent for a couple of example galaxies. So the important part for understanding galaxies is that we attribute the metal-poor globular clusters to galaxy halos, and the metal-rich globular clusters are traces of the build-up of bulges. And there are several reasons for us believing that to be true. For example, the metal-rich globular clusters, shown here as the red points, trace the galaxy starlight. This is an example from work led by Jay Strader. The dashed line here is the galaxy starlight in M87, the massive elliptical in Virgo, and the red points are the red globular clusters, the metal-rich globular clusters, and the blue globular clusters are more spatially extended. And this is a typical result. If we look at metallicity distributions, the peak in the bimodal distribution, the peak metallicity of the globular clusters correlates with host galaxy luminosity for both the metal-rich and the metal-poor star clusters. The relation that links globular cluster metallicity to host galaxy luminosity is very much like the relation that links galaxy metallicity to galaxy luminosity. So yet another reason for linking the metal-rich globular clusters to the galaxy starlight. So having said all that, that was the background, one of the things that we're doing is using the fact that we have 3 tracer populations for a galaxy's gravitational potential. We have the stars, the blue, the metal-poor globular clusters, and the metal-rich globular clusters. And we can use the fact that there are 3 tracer populations doing Bayesian MC-MC analysis with anisotropic genes models to examine a number of fundamental parameters about the galaxies. And I'm showing just the result of the pilot study for NGC 1407, another massive elliptical galaxy. And using this method, we can constrain the total mass very well. We'd like to, particularly in light of all the talks we've heard so far today, we'd like to say something about the central slope of the dark matter. But there's a degeneracy between that slope and the stellar mass to light ratio. So the way that we're trying to, and that's shown up here, which is dark matter slope against mass to light ratio in the B band, the way we're attacking that is with a new project where we're using Keck again, this time errors, to measure radial variations in the initial mass function. And we're getting those IMF indicators from the spectral lines. This is work that I'm doing with Charlie Conroy and Pete Van Dockum. You can see, again, we've done several galaxies. This is one of them at the same galaxy, NGC 1407, where you can see that the mass to light ratio has a steep central gradient. This is radius mass to light ratio over the Milky Way mass to light ratio. And this suggests we have a bottom heavy mass to light ratio and implies that in this galaxy we have a dark matter core. So this is just a bit of a taster. Asher Wasserman, who's a graduate student working with me here in Santa Cruz, is extending this Bayesian analysis, making it more sophisticated, increasing the number of free parameters from 7, we have 9 now, and applying the method to more galaxies from our sample. One intriguing result that's come out of this work and some earlier versions of it is looking at the globular cluster orbits. We find this rather surprising result that the blue globular clusters, the metal-poor ones that trace the buildup of the halo predominantly, the galaxy halo, those are mostly on tangential orbits. And of course, this is at odds with theory, which would predict radial orbits based on hierarchical growth by accretion. And so you can see these are the blue globular clusters, these are radial orbits, tangential orbits, here are the red globular clusters. So you can see the blue ones predominantly have tangential orbits, the reds are mixed, and this is roughly what you'd expect from theory. So that's something also we're pursuing in more detail, taking careful account of outliers and so on, but this is an intriguing result. So, mass distributions in galaxies. This is work led by Abusola Alabi, a graduate student that's working with Duncan Forbes, and the rest of us, of course. He's looked at 23 of our slugs galaxies and has looked at the mass distributions within 5 effective radii and also the mass distributions beyond that radius. And he's used the tracer mass estimator method from Watkins et al. And based on 3,500 globular cluster spectra, which extend out to 10, 13, and 15 effective radii for the low mass, the intermediate mass, and the high mass objects, we have these spectra with the very impressive velocity resolution that DMOS provides of 15 kilometers a second. So the results are up here. This is kind of a busy plot, so just look at this one. These are just different panels for different mass to light ratio assumptions. So this is the fraction of dark matter within 5 effective radii against total mass. And we find that compared to simple galaxy models, these are WMAP and Planck cosmologies shown in those two lines. The low mass and the high mass galaxies accord with those models, but the intermediate mass galaxies seem to have low dark matter fractions, only about 0.3. And the stellar mass that corresponds to is about 10 to the 11 solar masses. So this does seem to be consistent with the simulations of Wu et al., where the dark matter is modified by...
appeared to be roughly the total mass, so the stellar mass.
Well...
What stellar mass?
It should be about 10 to the 11. It's a bit more total mass. Total mass is a bit higher there.
10 to the 11 is, we only find massive galaxies, mostly looking at 10 to the 11.
Well, I guess it's on this scale, lower, middle, and upper. So the galaxies around that mass. Okay, so we can move the boundaries if you like. But anyway, so yeah, so that's a hint that these intermediate mass galaxies have been modified by interactions with baryons. Indeed, it looks like these may have more diffuse dark matter halos, and again, that possibly indicates that they were assembled relatively late. I want to just quickly introduce ultra-compact dwarfs, because you'll hear a bit more about these later. Ultra-compact dwarfs are dwarf galaxies we've known about for more than 15 years, and in all that time, there's been an argument about whether they're predominantly stripped galaxy nuclei or large star clusters. And you can sort of see the problem. The top two are ultra-compact dwarfs they look like globular clusters, they're just bigger. And these down here are globular clusters. These two both have the same brightness. These two both have the same brightness. So if you look at a plot of size, half-light radius in this case, against magnitude, these would be globular clusters, typically 3 parsec half-light radius. And as you shoot up in this direction and you're going towards massive galaxies up here, like compact ellipticals and bright ellipticals, and this region in here is occupied by ultra-compact dwarfs. So they're basically big, globular cluster-looking things. But it's unclear where this boundary really lies. I'll explain why that's important. So there are some smoking guns of an origin as a stripped galaxy, because, for instance, in one of the slugs results was discovering the then densest galaxy. This is a galaxy in M60, galaxy near M60. It's called UCD1. And if you look at a normal, quote unquote, UCD, so something that's bigger than a typical globular cluster, that's it there. You can't see it very well. And here is the then densest galaxy. We've several times broken our own record since then. But this, at the time, was the densest galaxy. So 2 times 10 to the 8 solar masses, a size that's too large to make it a typical globular cluster. And the interesting part of this is that with follow-up AO, adaptive optics observations, we were able to show that this little tiny galaxy hosts a 21 million solar mass black hole. Just to give you a comparator, the Milky Way's central black hole is only 4 million solar masses. Thanks. So that's you don't need to be a deep thinker to realize that this object used to be a much more massive galaxy. And in fact, there's a nice little simulation that Holger Baumgart did for us where you see the original galaxy coming in and getting stripped once it's in the proximity of the M60 gravitational potential. And then at the end of this simulation, you'll see all the shells and things that you often see. You'll wind up over here where the UCD has been detected. And the point is obviously that these objects, if they are indeed generally stripped galaxy nuclei, offer us the opportunity to really unravel the accretion history of things that have built the galaxy halo. So, well, now that we know these things are there and they might be very interesting, we've been looking for them, and some of the UCDs are embedded in streams, and some of these streams have their own globular clusters. So this allows you the opportunity of modeling in some detail this whole build-up of the galaxy halo. And just to reinforce another point, here are two systems we've looked at where the stream is a Sagittarius stream analog, and the nucleus is an omega-sen in formation, which raises the question of how many of the most massive globular clusters are in fact UCDs. So that there's a very fuzzy boundary there between star clusters and UCDs. So we can have a look at various stellar populations parameters to understand better these relative numbers of star cluster and galaxies, metallicity age, alpha, for instance, and there's another survey we're involved in that's doing stellar populations in UCDs. That's all too complicated to look at, so just have a look at the metallicity one. So again, like I showed you before, these are the globular clusters. These are massive ellipticals, compact ellipticals, dwarf ellipticals, dwarf spheroidals. And you can do some really crude calculations where you use the width of the stream to give you a crude idea of the size of the progenitor of galaxy. You can use the stream luminosity as a crude estimate of the progenitor mass. And then you can stick some trajectories, stripping trajectories on here, and look at the relative stellar populations and see if you believe that a galaxy up here could be stripped to an object down here. And you feel pretty good about this possibly working. You can also do more sophisticated simulations, and people like Pfeiffer and Baumgart have done that, and they conclude that only a minority of the UCDs are in fact stripped nuclei. So this is a very active and somewhat controversial area. So lastly, my last couple of minutes, I'm just going to introduce ultra-diffuse galaxies. These are objects that I'm actually very excited about at the moment, and we are trying to figure out whether ultra-diffuse galaxies are failed L-star galaxies or puffed up dwarf galaxies. And here's a UDG, which if you can barely see it, it's shown to scale with M31 over here and a dwarf elliptical over there and a compact elliptical there. And this UDG is actually 4 kiloparsecs, so it's a giant galaxy size with a dwarf galaxy luminosity. So this is sort of the question of the day. And thousands of these objects have been discovered through imaging in COMA, and they lie up here on this plot of size versus luminosity. So down below here would be the globular clusters if they were on this plot. They're not. Here are the top end of the UCDs, the compact ellipticals, the dwarf spheroidals, and the UDGs are up there. So we took spectra at Keck and confirmed that this particular UDG was at the COMA distance, and by inference the thousands of UDGs that have been discovered in coma are also associated with coma, properly associated with coma. And they're scattered throughout the coma cluster. We don't see any tidal disturbances around these things. Now, this is a real tour de force for you theorists because these things are extremely faint. So it's not easy to study the UDG starlight directly. But luckily, these things often have globular cluster systems. And this opens up an enormous opportunity to measure their total masses, because you can use the globular clusters if you can get spectra of the globular clusters, and they're much, much brighter than the UDG starlight, you can use them to measure a dynamical mass, and you can also use their total number of globular clusters as a second total mass measurement, because it's quite well established now that the number of globular clusters is directly linked to the total mass of a galaxy. So this was shown in this first foray into this work led by Mike Beasley, where both the dynamical mass and the mass based on the total number of globular clusters gave a consistent result and showed that this UDG is very heavily dark matter dominated. This is actually a Virgo UDG. Virgo has many fewer UDGs than coma does for mysterious reasons, and they tend to be a little bit smaller. Now, coming up next, Aaron Romanowski is going to be telling you about our more recent work on UDGs and some of the really exciting results that are weighing in on whether or not these are failed giants or puffed up dwarfs. So I'll just summarize quickly. I've told you about the bimodality, that the globular clusters have subpopulations that are distinct in metallicity and kinematics. The metal-rich ones trace the buildup of bulges. The metal-poor ones help us understand galaxy halos. We're doing dynamical modeling, multi-population dynamical modeling, and getting independent constraints on the dark matter distributions in galaxies. We seem to be finding tangential orbital anisotropies for the blue ones, which they should be predominantly coming in by accretion, so that's interesting. We're getting low dark matter fractions for intermediate mass galaxies. Possibly this means they assembled late and there's been baryonic interaction with the dark matter. We've got new classes of UCDs. We find faint ones as well as bright ones. And there's mounting evidence that many of them are stripped galaxies. And this allows us to have a really interesting insight into the occurrence of minor mergers. So UDGs, are they failed L-star galaxies? I think there's interesting evidence that they are. They certainly seem to be dark matter dominated where we can make the measurements. But you'll hear more in the next talk from Aaron about that. Alexa Vayom is going to be talking more about UCDs also this afternoon, and her new work on stellar evolutionary modeling. Duncan's talking on Thursday about SLUG's results on ETG galaxy assembly and relating them to NARB assembly classes. And Ignacio Martin Navarro, is going to talk about stellar populations and IMF variations. So, thanks.
Okay, questions for Jean?
Is it possible, a question about the tangential orbits of the, is it possible that only those survived from stripping? And
yeah, that's an interesting question. We were just talking about that earlier. Yes, I mean, if you've gotten rid of the ones that plunged in close to the center, you would have predominantly tangential orbits. I think the tricky part is that these are actually measured out to very large radius in galaxies. So I think the closer in you go, the more plausible it is that you're seeing that kind of culling due to the passage near the centre. I think it becomes tenser as you go further and further out. And these globular cluster measurements go out to very many effective radii. So,
further questions? Well, maybe while Aaron sets up, I can ask. What do you think the crucial tests will be for the failed L-star galaxy versus the dwarf galaxy? Is it getting more globular cluster systems for these? Is it finding the spatial clustering of them? What do you think the best way forward will be?
Well, I think the fact that they're distributed all through the Virgo cluster, the Coma cluster, so close in and far out, that's one very interesting point that will help us understand how they originated. But we're doing a survey now to see how many of these systems have globular clusters, look at the globular cluster numbers, and eventually, of course, get spectra for more systems of the globular cluster system. So in the end, we'll be able to say how many of these are dark matter dominated and how heavily dark matter dominated. The one case that I showed, and Aaron will be talking more, it's a very extreme result. They're heavily dark matter dominated, which makes sense to me. I mean, how thousands of them could survive in coma unless they were dark matter dominated, I don't know. But
very interesting.
Yep.
Okay, let's thank Jean again.
We already have about 60 papers that have resulted using data from this survey, and I invite you to have a look at the website here to see the wide variety of things that we're doing with these data. So there's a couple of things you need to know about globular clusters as discrete traces in the galaxy formation context. One is that they're bimodal in metallicity. This is a color histogram up here, clearly bimodal. They're also bimodal in metallicity. These are spectroscopically determined metallicities. And this tells us try and set the stage for a number of topics that will come up in talks that will be given by group members later on in the week, this afternoon and Thursday, in fact. So one of the reasons we really like globular clusters, or among the reasons we really like globular clusters for understanding galaxy formation, is, of course, because almost all galaxies, except the very tiniest ones, have globular cluster systems. And the premise is that globular cluster formation accompanies all the major star-forming episodes in a galaxy. Ah, there we are, good. I can go. So I'm going to be talking about what we can learn about galaxy formation by using information from discrete traces in concert with the information we get from the galaxy starlight itself. And this work's done under the umbrella of the SAGES collaboration, and these are many of the collaborators on this project, and the people in yellow here are at this meeting. So I'm going to survey done with Subaru and Keck, particularly the DEIMOS spectrograph, of 25 nearby early type galaxies. And these galaxies have a range of fundamental properties. And we're able to look at the field stars out to 3 effective radii and the globular clusters to 10 or more effective radii in these galaxies. So we get 2-dimensional kinematic and metallicity maps with which we can compare to the theoretical models. So we completed the observations just this year and history. They're bright compared to the underlying galaxy starlight, and once formed, they're really unchanging. They're formed at very early times, they're unchanging, and are along for the ride, if you like, with all of the mergers and acquisitions that come to build the galaxies we see today. So because they're bright, we can do spectroscopy to pretty significant distances. So everything I'll be talking about has come out of the slug survey. This is a